The most recent ice age lasted from around 2.65 million years ago to 11,700 years ago, when the Pleistocene epoch ended and the current Holocene epoch began. The last glacial period and last glaciation are common names for this ice period. Quaternary glaciation, which began about 2.58 million years ago and continues to the present day with ice sheets still existent in Antarctica and Greenland, is the bigger ice age complex of which this was a part. There have been milder interglacial times like the current Holocene, during which ice sheets have retreated inside this larger quaternary glaciation. For most of the previous 2.6 million years, however, Earth's climate has been substantially colder than today, with continental scale ice sheets extending to cover large portions of North America, Europe, and Asia during peak glacial eras. The most recent cycle of widespread glaciation, known as the last glacial period, peaked roughly 20,000 years ago at the last glacial maximum and has been retreating for over 10,000 years. When the last ice age began and ended, there were periodic ice ages and warmer interglacials within the Pleistocene epoch. During glacial times, ice sheets grew, whereas during interglacial times, they shrank. A recent glacial peak occurred between 26,500 and 19,000 years ago and is called the last glacial period. Before it, 13,000 to 114,000 years ago, there was an interglacial period called the Eemian. Ice ages are characterized by periodic cooling and warming phases known as glacial and interglacial periods. The beginning and conclusion of glacial eras are influenced by variations in Earth's orbit, solar output, atmospheric greenhouse gas concentrations, ocean circulation alterations, and volcanic activity. There are additional feedback systems at play. For instance, expanding ice sheets cause greater cooling and glaciation because of the increased surface reflectivity, albedo, that results from more incoming solar radiation being reflected into space rather than absorbed. This positive feedback loop amplifies the initial cooling impacts from decreasing solar insolation, greenhouse gases, and other causes. The last glacial maximum, or LGM, is the point in time when global ice volumes were at their maximum. Maximum ice volume is estimated to have happened sometime around the year 20,000. This event took place between 26,500 and 19,000 years ago. Ice sheets covered parts of North America, Europe, and Asia during the LGM. The Cordilleran ice sheet covered British Columbia, Washington, Oregon, and Idaho in the west, and the Laurentide ice sheet reached as far south as Illinois in the United States in the east. British Isles, Scandinavia, Poland, Germany, and the rest of Northern Europe were all covered by the Fennoscandian ice sheet. The European Alps, the Pyrenees, the Caucasus Mountains, and the Sierra Nevada in California were all home to alpine glaciers. During the LGM, around 125 meters less water was believed to be locked up in these continental ice sheets, resulting in lower world sea levels. This effectively joined land masses like Siberia and Alaska by exposing enormous expanses of continental shelves normally underwater. Due to the reduced amount of water in the world's oceans, land bridges were also created between Australia and New Guinea, Britain, and the rest of Europe. During the last glacial maximum, roughly 30% of Earth's land area was ice covered. The ice sheet's added weight was sufficient to depress the Earth's crust underneath. The Laurentide ice sheet in North America extended down to where Illinois is today, while the Cordilleran ice sheet covered what is now British Columbia, Washington, Oregon, and Idaho. The British Isles and much of northern Europe were frozen due to the presence of the Scandinavian ice sheet in Europe. Alpine glaciers originated in the mountains of Europe, the Pyrenees, and Spain and California, respectively. During the last glacial maximum, when these ice sheets were at their largest, they trapped enough water to reduce world sea levels by about 125 meters relative to modern-day levels. Beringia, which lies between Siberia and Alaska, is one example of a land bridge made possible by the exposure of vast expanses of continental shelf. The last glacial period ended about 11,700 years ago, when the Earth's climate began to rise around 20,000 years ago, ushering in the present interglacial period, the Holocene. After expanding during the last glacial maximum, continental ice sheets retreated globally as the Earth entered the warmer Holocene epoch. Multiple variables contributed to this deglaciation, including warmer temperatures, altered precipitation patterns, and catastrophic floods caused by glacial outbursts. There were times when ice sheets melted and broke apart, accelerated, flooding the oceans with fresh water and changing how the water circulated. Around 14,500 years ago, sea levels rose dramatically due to the rapid discharge of glacial meltwater into the North Atlantic, reducing the efficiency of the Atlantic's meridional overturning circulation. This largely triggered the older Dryas cold period, which lasted about 150 years. Smaller mountain glaciers and ice caps were the first to melt as the Earth continued to warm over thousands of years. Greenland and Antarctica both had ice sheets that had yet to melt completely. Between 14,000 and 7,000 years ago, there was a significant deglaciation in North America. By about 6,000 years ago, only Greenland and Antarctica still had significant ice sheets. The enormous Laurentide ice sheet in Canada and the Eurasian ice sheet had retreated. The sea level rose by more than 100 meters due to this worldwide melting, compared to its Ice Age low point. Throughout the Holocene, ocean currents and regional climates were affected by pulses of meltwater from melting ice sheets. There were times when the ice melted quickly, leading to massive inundation. For around 150 years after 14,500 years ago, the climate in the northern hemisphere was much colder than usual because of a sudden surge of glacial meltwater into the North Atlantic. As the planet warmed, tiny ice caps and mountain glaciers melted away first. Both Greenland and Antarctica held on to the remnants of their continental ice sheets. Major ice sheets completely receded from Eurasia and North America around 6,000 years ago. Global landscapes were profoundly altered by the erosion and deposition of slit brought on by the advances and retreats of enormous ice sheets during the last glacial epoch. Moving ice sculpted characteristic glacial landforms such as cirques, arêtes, horns, U-shaped valleys, hanging valleys, and fords along coasts in alpine locations with valley glaciers. Meanwhile, the continental ice sheets flattened the land and layered on tons of glacial till, clay, gravel, and other debris, changing the landscape in many places. This resulted in gently undulating plains, hills, and landscapes developing throughout the ice-covered northern regions of North America and Eurasia. As it spread across northern North America, the Laurentide ice sheet scoured the landscape with its sharp edges. Glacial erratics, which are enormous boulders, were carried great distances by moving glaciers and then dumped hundreds or thousands of kilometers away from their original location. Lakes are abundant throughout the Great Lakes and much of Minnesota and North Dakota because the landscape was cut away by glaciers, leaving behind depressions that filled with water when the ice retreated. Northern Europe, for example, displays classic U-shaped valleys, fords carved along Norway's coastline, and plentiful lakes left behind by receding ice sheets across Finland, Sweden, Germany, Poland, and beyond. Similarly, the terrain features of the Alps and other alpine regions show clear signs of ice in the past. The Laurentide ice sheet reshaped landscapes in North America by scraping away topsoil and rock. Large boulders known as glacial erratics were carried hundreds or thousands of kilometers by ice and eventually dumped far from where they originated. Lakes and marshes fill depressions created by glaciers across Minnesota and the Great Lakes region. Similar U-shaped valleys, fords along Norway's coast, and numerous lakes left behind by melting ice sheets can be found all over northern and central Europe. Evidence of widespread glaciers remain in the Alps and other mountain ranges. Earth experienced a gradual cooling trend that reached its maximum extent during the last glacial maximum. As atmospheric circulation patterns shifted, average global temperatures dropped by 4 to 7 degrees Celsius, resulting in widespread aridity. The climate throughout North America and Europe was more akin to the tundra or the Arctic desert. The number of plants and trees was low. Climates in the non-glaciated areas were dry and windy, with minimal annual precipitation. The glaciers that melted from the mountains blocked the rain from reaching the continent's heart. The upwelling and productivity in the North Atlantic, as measured by marine cores, have significantly decreased. The considerable cooling trend around 115,000 years ago reached its apex during the last glacial maximum, roughly 20,000 years ago. As atmospheric circulation patterns evolved in response to the ice sheets, global average temperatures dropped by 4 to 7 degrees Celsius, resulting in widespread aridity. It was mostly tundra or polar desert across North America and Europe, with very little flora and almost no trees. Reduced precipitation and significantly windier conditions affected even regions not completely covered by ice sheets. As they melted, mountain glaciers built barriers that prevented rain from reaching the dry centers of continents. Although the equator saw less impact than higher latitudes, tropical rainforest did shrink. At greater elevations, such as those found in the Andes of South America or the mountains of East Africa, temperatures and humidity were lower. The tropical rain belt shifted southward as the Arctic ice sheet grew. During the last ice age, dunes formed throughout Asia, the Middle East, and the American Southwest, and the Sahara Desert grew dramatically. Evidence from ice cores and ocean sediments indicates widespread deserts are the source of periodic dust storms. Colder surface waters and the insulating effects of sea ice expansion are believed to have lowered upwelling and biological production in the ocean, as evidenced by marine sediment cores in the North Atlantic and around Antarctica. Ecosystems were drastically altered by glacial temperatures and the direct effects of moving ice sheets. Woolly mammoths, mastodons, reindeer, musk oxen, snowy owls, and woolly rhinoceroses flourished in the harsh climate. North American horses are just one example of a species that declined or went extinct. At mid-latitudes, spruce, fir, and lurch have mostly supplanted cold-intolerant trees like oak, hickory, and beech. The Canadian boreal forest and the northern Eurasia tundra were the dominant biomes. Because of decreases in precipitation, grasslands spread throughout the interiors of continents. Extreme cold and the spread of ice sheets during the last glacial period caused widespread shifts in the world's ecosystems. Woolly mammoths, mastodons, reindeer, musk oxen, snowy owls, and woolly rhinoceroses were a few of the large creatures that did well in the frigid temperatures and the tundra or steppe settings. Like many other species that couldn't handle the climate, the North American horse went extinct or had its population drastically reduced. In the middle latitudes, spruce, fir, larch, and other conifers have largely supplanted cold-intolerant tree species, including oak, hickory, and beech. The northern parts of North America and Eurasia were covered in boreal forests and tundra. The cold and dry circumstances encouraged the growth of grasslands in the interiors of the continents. The Bering land bridge between Siberia and Alaska created far-reaching ecological effects because it facilitated the movement of plants and animals between Asia and North America. The exposed seafloor allowed many Asian mammal species, including camels, bison, and mammoths, to migrate to North America. Surprisingly, few mammal species have traversed the bridge backward. Major shifts also occurred in marine habitats. In contrast to the reduction of warm water creatures, cold water plankton species flourished. Changes in sea level and ice sheet size displaced coastal marine habitats like kelp forests. During glacial periods, people could occupy new areas of the continental shelf made possible by lowering sea levels. About 300,000 years ago in Africa, Homo sapiens first appeared. Somewhere in the range of 100,000 years ago, populations of anatomically modern humans began migrating out of Africa and into Eurasia, where they encountered earlier hominins such as the Neanderthals. Neanderthals and other ancient Europeans hunted reindeer and other cold-adapted prey. They wore animal skins for insulation and lived in caves and rock shelters. Prehistoric humans likely used fire for cooking and heating and used animal hides and furs as clothes. Around 115,000 years ago, when the last glacial period started, life became extremely difficult for these ancient populations. To be warm, Neanderthals and other hominins developed techniques like cave dwelling, rock overhanging, and sewing animal hide into clothes. According to excavations, they used bone, antler, and ivory to make implements. The ability to manage fire allowed for both heat and food. Nevertheless, despite these changes, ancient human populations were tiny throughout the previous ice age, in contrast to the expansion of modern human populations after the ice age ended. Cold-adapted species such as the Neanderthals may have gone extinct around 40,000 years ago due to a lack of resources and an inability to find enough food to survive the extreme temperatures. In contrast, as the ice sheets withdrew around 40,000 years ago, modern humans swiftly extended into the warming landscapes anatomically. Hunting became easier and clothes could be made faster because of better instruments like spears, needles, and harpoons. Humans' cognitive and communicative advancements may have given them a survival edge, and developments in society, such as cave art, may be a reflection of that. Around 41,000 years ago, individuals with fully developed skeletons and the ability to use complex tools and weapons, such as spears, migrated to Europe. Herds of animals led humans into areas made livable by melting ice caps. Humans crossed the Bering Land Bridge into North America some 13,000 years ago, expanding fast across 2 continents as the glaciers retreated. During the Ice Ages, glaciers and ice sheets at poles and mountains grew to unprecedented sizes. These extended cold spells have occurred frequently throughout the Quaternary Glacier, which spans at least the past 2.6 million years. The tremendous glacial interglacial cycles that have shaped Earth's recent past have left many wondering what causes these climactic shifts. Scientists have identified several methods to alter Earth's energy balance and hence initiate and terminate ice ages. The Quaternary Ice Age cycles have been linked to small shifts in Earth's orbit around the Sun. As a result of these orbital changes, the amount of solar radiation that certain latitudes get at various times of the year varies. Even a slight shift in solar energy can trigger a tipping point in the climate system. The effects of periodic changes in eccentricity, obliquity, and precession on solar radiation patterns were initially documented in the 1920s by the Serbian astronomer Milutin Milankovic. The eccentricity of Earth's orbit around the Sun describes the gradual change in shape from a largely circular orbit to a somewhat elliptical one that occurs in roughly 100,000-year cycles. The obliquity of Earth's axis varies in 22.1 to 24.5 degree increments over roughly 41,000-year periods. Precession describes the 23,000-year swaying of Earth's rotating axis. These orbital cycles affect the seasonal and latitudinal distribution of the Sun's energy reaching Earth. Seasonal temperature differences between latitudes are accentuated at times of higher eccentricity, considerable axis tilt, and specific phases of precession. Throughout thousands of years, even modest variations in average insolation can set in motion the feedback that ultimately determines whether an ice sheet expands or contracts. Greenhouse gases, which include carbon dioxide, methane, and water vapor, play a crucial role in maintaining stable surface temperatures on Earth by absorbing radiant heat from the ground and upper atmosphere. Changing levels of greenhouse gases over time are also a major factor in glacial interglacial transitions. From interglacial highs to glacial lows, CO2 levels decrease by around 30% in ice core data. The colder oceans absorb more CO2 during glacial eras, while carbon is stored in the growing terrestrial biosphere. The expansion of ice sheets also led to the drying up of significant sources of atmospheric methane, such as tropical wetlands. The cooling effect of other causes, such as orbital cycles, is amplified by the reduction of greenhouse gases. Deglaciation is largely driven by the feedback of increasing CO2 and methane as the Earth's temperature warms. Although CO2 levels rise after temperatures have begun to rise, this suggests that greenhouse gases reinforce rather than initiate the end of ice ages. Orbital shifts and changes in ocean circulation probably trigger initial warming. Variations in solar activity did influence glacial interglacial eras, contrary to earlier beliefs that changes in solar irradiance were too modest to contribute significantly to quaternary climate shifts. Cosmic ray and ice core measurements of beryllium isotopes show that the sun's magnetic field strength has varied significantly during the past million years. Higher levels of solar activity are associated with greater deflection of galactic cosmic rays away from Earth. When the sun is more energetic, fewer sunspots appear. Reduced sunspot abundance increases energy production because sunspots are colder than the surrounding photosphere. According to estimates, total solar irradiance may have varied by as much as 6 watts per meter squared between the last glacial maximum and the late 20th century. As recent computer simulations have shown, the temperature response to orbital oscillations, greenhouse gases, and other causes may have been exacerbated by changes in irradiance. Changes in ocean circulation patterns have had substantial effects on ice age weather. Today, heat and salt are distributed globally via the Atlantic Meridional Overturning Circulation, or AMOC, which moves warm water north and returns cold deep water south. During glacial times, AMOC was considerably weakened. The salinity and density of northern Atlantic surface waters decreased, possibly due to the entry of fresh meltwater from melting North American ice sheets. The movement of warm water northward via convection currents was impeded. Northern hemisphere ice sheets expanded due to the colder sea surface temperatures. The creation of Antarctic bottom water, the engine that drives global deep ocean circulation, was also temporarily inhibited during glacial epochs. Wind and sea ice changes affected surface buoyancy and slowed bottom water generation. Since more CO2 could be stored in the deep ocean due to the slowed circulation, atmospheric greenhouse warming was mitigated. Oceanic entryways played a role in shaping circulation patterns. As a result of Bering Strait's opening, more Pacific freshwater is entering the Arctic, while less heat is transferred between the Pacific and Indian Oceans via Indonesia. Volcanic eruptions that send aerosols into the stratosphere can temporarily lower global temperatures, sometimes for as long as a year after a particularly large eruption. Ice core data suggest an uptick in volcanic activity before the last glacial maximum and during other times of rapid glacial expansion. Large eruptions may have temporarily amplified cooling, which could have contributed to ice sheet expansion during orbital eras suitable for glacial. CO2 is also removed from the atmosphere on geologic timescales by weathering volcanic materials. Over millions of years, increased global volcanism reduces atmospheric CO2 and causes long-term cooling. Chemical weathering rates are boosted by the uplift and erosion of mountain chains worldwide, which may play a comparable impact. Although orbital changes, greenhouse gases, solar output, ocean circulation, and other factors all contribute to ice age cycles, the effects of these elements are dramatically amplified by intrinsic instabilities and feedback loops within the climate system. A net cooling imbalance develops in the global energy budget as incoming solar energy decreases and greenhouse gases like CO2 and methane are reduced. However, due to the ocean's enormous thermal inertia, temperature changes lag significantly behind the forcings. It takes a long time to cool down the ocean's large volume of water. Positive feedback mechanisms quickly accelerate cooling into full glacial conditions as susceptible components of the climate system, including sea ice, snow cover, and land ice, approach critical tipping points. Combined with initial perturbations in the climate system from external climatic forcings, these instabilities and feedback loops are a major factor in driving the climate system into an ice age. Sea and land ice eventually reach critical tipping points, triggering powerful feedbacks that push runaway cooling into full glacial conditions. As highly reflecting ice sheets expand, they set off the ice albedo feedback. Drying out the planet causes a drop in carbon dioxide levels. As sea ice expands, it acts as an insulator, changing the direction of ocean currents. During periods of deglaciation, additional feedback and instabilities push the system back into interglacial warming. A single factor does not cause Earth's climate transitions between glacial and interglacial phases. Instead, the oscillations between smaller ice ages and warmer interludes that have typified the Quaternary period are driven by the intricate interplay between external climate forcings, internal system dynamics, and various feedback processes. Researchers are still trying to piece together the whole picture of the complex cycles that have modeled Earth's ecosystem in recent eons. Over the past 2.6 million years, the Earth's climate has fluctuated with the help of the quaternary glacial interglacial cycles. The present interglacial period, the Holocene, has lasted for roughly 11,700 years. May we enter a new ice age in the not-too-distant future? Or will the next glaciation be indefinitely delayed by the human-caused warming of the Anthropocene era? Researchers are trying to predict when the next ice age will begin and how human activity can change natural cycles. When should the next ice age begin based on these natural factors? The typical time between Pleistocene ice eras was 40,000 to 100,000 years before human interference. Interglacial periods, on the other hand, varied more widely in length, from about 10,000 to 30,000 years over the past 500,000 years. Within this normal range, the current Holocene interglacial can be found. Milankovitch cycles, cyclical oscillations in Earth's orbit and axis tilt, set the tempo for glacial and interglacial periods. Between now and 26,000 years from now, summer insolation in the northern hemisphere is expected to begin drop at a rate favorable to the onset of glaciers. However, the varying lengths of interglacials cannot be explained by orbital cycles alone. Whether or not a particular drop in insolation causes a climate system-wide cool down and the onset of an ice age depends on other internal variations. This includes the long-term decline in atmospheric CO2 due to natural geological and oceanic carbon cycle processes. The next glaciation might start anywhere within the next 50,000 years, although the margin of error is huge. The onset has always lagged behind the orbital forcing by a considerable amount. There are several lines of evidence suggesting that the current interglacial will last for a much longer time than would be predicted by just orbital factors. The next ice age may be postponed for 100,000 to 500,000 years due to ongoing human global warming. Human activities over the past 2 centuries have resulted in the release of greenhouse gases to the atmosphere at quantities not observed in nature during the whole Quaternary period. The atmosphere's ability to trap heat increases by a factor of 2 to 3. Natural processes may take up to 100,000 years to remove the extra CO2 people have generated. Even the sun's rays have leveled out recently. It will be another 7,000 years until conditions are right for glaciation in the northern hemisphere. High carbon dioxide levels prevent glaciers from forming because they hinder the natural decay of greenhouse gases. The dramatic melting of the Laurentide and Eurasian ice sheets has also changed the reflectant of the Earth's surface and likely other factors, which may have prevented reglaciation in favor of an extremely lengthy interglacial. Some researchers have hypothesized that human activity has pushed the climate into a radically different regime that would permanently suppress glacial and interglacial periods. Past epochs such as the Pliocene, which lasted 3 to 5 million years ago, saw elevated CO2 levels and comparatively little ice in the northern hemisphere. However, in most cases, their durations fell short of what might be expected from the persistence of human-caused effects. Maintaining a CO2 concentration of 240 to 260 ppm for at least 100,000 years and closer to 400,000 years is necessary to stabilize interglacial periods. Erosion of continental rocks may draw CO2 down after tens of thousands of years if CO2 is stabilized at current levels. This indicates that constant artificial carbon sequestration may make it easier to maintain the existing climate regime across geological timeframes. Predicting a changed glacial cycle due to human activity is uncertain. However, without sustained human intervention, natural orbital force is expected to re-establish itself at some point. As a result, the Holocene will give way to fresh glacial interglacial cycles once human influences have faded. Although global warming is likely over the long term, some researchers have suggested that human greenhouse gas emissions might cause a short regional cooling event in the future centuries by altering ocean circulation. In particular, the Atlantic overturning circulation could be slowed or stopped by an influx of cold, fresh meltwater from the collapse of the Greenland ice sheet. According to the models, this may result in a 10°C drop in temperature for Western Europe and some portions of North America in just a few decades. After 2 centuries, though, temperatures would rise again. Because of these natural forces, Earth's orbital changes may continue to drive glacial and interglacial cycles. However, due to the human-caused global warming in the past 2 centuries, a full ice age is unlikely to begin for at least 100,000 to 500,000 years. An important open question is how much longer elevated greenhouse gas concentrations and altered surface conditions may be maintained due to human influences. By constantly intervening to stop CO2 drawdown, an interglacial condition may be maintained, at least temporarily. Once human interference weakens, though, quaternary glacial cycles may return. One of the Earth's most spectacular examples of climate variability is the periodic advance and retreat of gigantic ice sheets across the northern hemisphere. Long, cold glacial periods have alternated with warmer, interglacial areas devoid of continental ice sheets on Earth for at least the past 2.6 million years. These ice age cycles have dominated the Quaternary epoch, the most recent being the last glacial period, known as the last glaciation. The intricate interactions between external climate forcings and internal feedback processes within the climate system are the root of Earth's ice age climate cycles. The seasonal and spatial distribution of incoming solar radiation is affected by minute wobbles and variations in the planet's orbit and tilt. The cooling effects of less sunlight are amplified in susceptible locations like the Arctic as significant greenhouse gases like CO2 and methane decline. When the global system is pushed past crucial tipping points, significant feedbacks like the ice albedo effect take over. This can be caused by various factors, included but not limited to shifting ocean currents, volcanic activity, and variations in solar output. Even while we don't fully understand what causes ice ages to begin and end, their effects on the world's ecosystems and surroundings are undeniable. Canada, the northern United States, northwestern Europe, and Siberia were covered by ice sheets up to 3 kilometers thick during the last glacial maximum, roughly 20,000 years ago. Because of the massive amount of water trapped in these continental glaciers, sea levels dropped by around 125 meters compared to today. This caused major changes to coast and exposed land masses that are normally submerged, such as Beringia between Alaska and Siberia. Rather than gradual cooling, the transition to the last glacial maximum was marked by extreme climate swings. In some cases, temperatures dropped by more than 10 degrees Celsius in just a few decades. Ecosystems as a whole were pressured to relocate quickly or perish. Some animals, like the woolly mammoth, did well in frozen meadows and tundra, but the vast majority became extinct. Possibly unable to upgrade their stone tools and fur garments to compete with those of Homo sapiens, the Neanderthals and other archaic human lineages went out. The end of the previous ice age did not occur along a single course, just as the causes were multifaceted. As the ocean currents shifted and the rains came down in torrents, some of the massive continental glaciers collapsed catastrophically. Sea levels rose and coastlines shifted throughout thousands of years as the climate warmed and ice sheets retreated toward Greenland and Antarctica. Because of this, forests could expand and grow farther north, and people could migrate beyond northern boundaries into the Americas. Major uncertainties surround the future of the current interglacial period in light of the significant climate shifts and biological transformations that defined previous ice age cycles. The orbital changes in greenhouse gas concentrations that drive glacial interglacial oscillations may allow Earth to experience them again. However, due to human-caused global warming during the past 2 centuries, another full-scale ice age is unlikely to occur within the next 100,000 years. The time that human impacts can maintain increased CO2 in changing surface conditions will determine what happens after that time scale. The Quaternary ice ages irrevocably altered our environment today, yet predicting the climate for the next tens of thousands of years is still a highly speculative endeavor. Their experiences have taught modern humans how the Earth's climate system has the potential to alter habitats, biomes, and social structures radically. More than anything else, they serve as a sobering reminder of the grave repercussions posed by artificial greenhouse gas emissions and planetary heating by demonstrating how sensitive the global climate is to even minor changes in inputs that aggregate over time. The end. Ice Age: History and Future. Written by Dwayne Buck. Narrated by Miles